Okay, hello everyone. Can you hear me well?
Yes.
Yes.
Okay, thank you. So
Yes.
my name is Cameron Ismaili, and I'm a professor at the University of Toronto and currently the chair of the Canadian Rock Mechanics Association, CARMA. Welcome to our fourth webinar, which is jointly organized by the CIM's Rock Engineering Society and CGS's Rock Mechanics Division and the Canadian Rock Mechanics Association, CARMA. Thanks for joining us today for this very interesting webinar on the application of appropriately complex in situ stress for numerical modeling in geomechanics and rock engineering. Our speaker for today is Dr. Kathy Kalinchuk. She has a degree in mining engineering from the University of Alberta, and she completed both her master's and PhD in geomechanical engineering at Queen's University. Dr. Kalinchuk is the president and principal consultant of Rock-Eng Company and an international rock mechanics expert with extensive experience in geotechnical and geomechanical engineering. She has contributed to geotechnical and ground control studies for more than 100 mines and mining projects around the world. And she's specialized in underground mining, operational rock engineering, and ground control. She's an expert in geomechanical mine design, induced seismicity, and also numerical modeling. So without further ado, let's get started. Kathy, the floor is yours, please.
Thank you very much for the introduction. I just want to confirm you can see my slideshow in the full presentation mode?
Yes, we do.
Yes.
All right, as introduced, I'm going to be talking today about in situ stress and making sure that when we're doing geomechanical design, we are accounting for natural complexities in our pre-mining stress states. As the title suggests, this talk does have a focus on numerical modeling, but I do want to point out that the concepts around in situ stress and making sure that we get it right is applicable, of course, to other design methods like analytical tools, the utilization of, and also empirical design. So it's a bit broader as well. Okay, so the lecture is motivated by our need to do a good job as geomechanical engineers at developing strategies, both strategic strategies and tactical strategies for mitigating ground control risks. My focus is on mining operations. But again, you could extrapolate the ideas I'm going to talk about today to managing geotechnical and ground control risks in civil and construction works as well. So to develop effective and economical risk mitigating strategies, we need to make sure as engineers that we have a solid understanding of the likely ground reaction mechanisms that will be encountered in our design execution. And having a sound understanding of the ground reaction mechanisms requires that we really have a comprehensive foundation for knowing what our boundary conditions are. And generally, well-defined boundary conditions, it has a reliance on numerical modeling. The contents of my lecture today, I will touch briefly on the influence of stress state on failure mechanism, just as some general background, leading into more detailed discussion about in situ stress. I will talk about design categories for geomechanical hazard management and inputs for our geomechanical design process. And coming out of a discussion of inputs, we will focus on in situ stress because this is often the most significant unknown that we have in our design process. And then I will speak to moving away from common practice for in situ stress estimating towards methodologies for best practice in applying in situ stress to our design, and a couple of case studies to demonstrate what this looks like, and then we'll summarize key points. So just some general background. Anticipating our failure mechanisms requires an understanding of our rock mass conditions and also an understanding of our stress conditions. So as an example, if you are in a highly fractured rock mass under relatively low stress conditions, our failure mechanisms tend towards raveling or chimneying style failure. Whereas if you take that same rock mass and you apply it to a high stress condition, then you tend to see squeezing or crushing behavior. So a completely fundamental change in failure mechanism according to the stress loading conditions. If we think about jointed rock masses, at low stress conditions, we tend to see wedge failures in jointed rock masses. And of course, wedge geometries can vary depending on the nature of our fracture fabric within a rock mass. Under high stress conditions, we tend to see much fewer wedge failures because in situ stress can actually work to clamp wedges in place. And so a rock mass tends to transition into...
Rinse your glass and my glass.
Oh,
Yeah.
I think somebody needs to maybe mute. Okay, so in jointed conditions, high stress, we're moving towards spalling and crushing failure. If you have massive rock with very few fractures or random fracturing, generally these are quite stable under low stress environments. And then in high stress conditions, of course, we move into spalling and crushing type behavior. So having an understanding of failure mechanisms, of course, is going to lead our decisions around design processes for developing ground control risk mitigating strategies. A little bit more background information. Geomechanical design can be categorized into two different methods. First of all, there is susceptibility-based design. And in susceptibility-based design, the general objective is to investigate the susceptibility of a geomechanical system to a particular ground reaction mechanism. This generally will achieve qualitative or semi-qualitative expectations for ground reaction or interaction of our ground with ground support systems. Typically, susceptibility-based design is going to lean quite heavily on global scale numerical modeling, as well as empirical design tools. The other type of design process that we can follow is mechanistic design. And in this case, we are investigating our understanding of fundamental failure mechanics. This allows us to achieve quantitative expectations for ground reaction or the interaction of our excavations with ground support systems. In this case, we're more often relying on local scale numerical simulations. And in some cases, analytical solutions can fall into this design category as well. Okay. Moving on. To develop strategic and tactical risk mitigating strategies often requires that we take a multi-scale design approach when we're doing geomechanical analyses. Multi-scale design processes ensure that we are looking at global susceptibility behaviors as well as local mechanistic analyses. The first step in multi-scale analysis generally begins with global modeling, which allows us to forecast global mine scale ground reaction, stress conditions. It allows us to evaluate the geological controls on our in situ stress state and our material competencies. The second step is looking at local mechanistic analyses. Local mechanistic analyses are quite often coupled with global scale evaluations, again, because we need to understand that broader geological context that's controlling our ground reaction. And then once you have an understanding of global susceptibility to hazard as well as local mechanistic exposure to hazard, we can develop a fairly holistic understanding of the spatial and temporal distribution of geotechnical hazards with respect to mechanism, as well as with respect to intensity for how failure mechanisms may manifest within an excavation. So it's a flow process there. When we are doing geomechanical design, there's a number of design inputs that need to be accounted for. And as part of our design process, we need to understand how different types of data sources and different types of design inputs have varying levels of confidence. So as an example, mine shapes and mine geometries are a piece of our design inputs that we have to rely on. And we have information about mine shapes and mine geometries based on design, three-dimensional design solids, and also from as-built surveys that come from our construction processes. Generally, we have fairly good confidence in our mine shapes as a design input for most mining applications. Of course, there are some scenarios where you lose confidence in your design shapes, and this generally occurs where you have failure that is of a substantial volume relative to your area of interest, and measurements of that full volume cannot be achieved. The next two pieces of input are our geomechanical domain models and our geological domain models. Geological domain models comes first on the hierarchy of design confidences. We collect information related to geological models from drilling, lab testing, geological mapping. Sometimes we rely on geophysical tools. And the tools that we use to characterize our geomechanical or geotechnical domain models are similar. We're using drilling, lab testing, mapping, etc. However, we tend to have a lot more uncertainty and lower confidence in our geotechnical models just based on inherent data limitations. The amount of geotechnical data that we tend to have for projects is often much less abundant than geological data that is available. The last component of design inputs that I have on this slide is our loading conditions. So loading conditions in the context of my lecture today focuses on in situ stress. You may also consider loading conditions such as groundwater, where water flow rates or pore pressures are impacting your design. And in some cases, we actually think about thermal loading as well as a boundary condition. So with respect to loading conditions, and again, with that focus on in situ stress, this is the area of geomechanical design that often, or almost always, has the lowest level of confidence. You can test in situ stress through instrumentation. You can infer it from literature. You can back analyze it through design verification procedures and design calibration processes. But generally, overall, we have the lowest level of confidence in our boundary conditions that we apply to geotechnical design. So focusing then on this component of design that we have the least amount of information on, we need to recognize that the pre-mining far field stress state in rock is very complex, and it is influenced by a number of factors. In situ stresses are imposed on a rock mass environment by the weight of our overlying strata, is influenced by both active and paleo plate tectonics. Glacial loading and glaciation events can have a significant impact on in situ stress, as well as large erosional events. So the distribution of stresses that are imposed in our rock mass with respect to magnitude and also tensor orientation can be very complicated over multiple scales. And then we have additional second and third order factors that will influence it on local scales as well. We see stress gradient and stress rotation changes as we go across lithological boundaries, as we go through geological structures. These are generally driven by stiffness contrasts and the natural strain history of our geological environment. Further, at a more local scale, we'll see significant variability in natural in situ stress controlled by heterogeneities in our rock mass. So the fabric of our rock mass and discontinuities can locally complicate our stress tensor conditions even further. So geomechanical engineering requires that we define the magnitude, the gradient, and the direction of virgin in situ stress states so that we can understand the influencing controls on our design process. And it can be very difficult to establish these metrics. To demonstrate the complexity in situ stress, there is a very well executed case study that was done by Andrew Lariche as part of his master's studies at Queen's University about 6 years ago. This case study was some work done for the Victoria Project, which is located in the Sudbury Basin. And during the feasibility study of the Victoria Project, there were 2 pilot holes that were drilled along the planned shaft alignment. So these are 2 geotechnical holes running from surface to 2 kilometers depth. And over the length of these holes, geological data was collected, geotechnical core logging, lab testing, all of the traditional data collection was done. And they also ran acoustic televiewer surveys over the length of these drill holes. Now, below about 900 meters depth, borehole breakout became quite common, and it was observed in the acoustic televiewer data. So for anybody who's not familiar, borehole breakout is the stress damage that accumulates around the periphery of a drill hole through rock. And so based on the geometries of the borehole breakout, Andrew was able to back calculate the stress magnitudes and the stress orientations over the length of these pilot holes below 900 meters depth. And the chart that I have shown in the middle of this figure is taken from some of his publications, and it demonstrates the complexity in situ stress magnitude. So I have depth shown here on the y-axis and principal stress magnitude shown in megapascals on the x-axis. These dashed lines in red and black illustrate what our expectation would be for in situ stress, for the horizontal components of in situ stress varying with depth in this area of the world. And these solid lines that you see here in red and black are illustrating the back calculated horizontal components of stress that Andrew was able to achieve. And you can see there is substantial variability in the magnitudes of stress along the profile of these drill holes. And we see substantial jumps in stress magnitude as we go across lithological boundaries or across geological structures. And some of these rapid changes in stress are in the order of 10 to 20 megapascals going across contacts. So not insignificant in terms of what we need to apply to our design assumptions. Now, despite the complexity that we know exists in virgin stress states in all geological environments, the example I show you from the Victoria Project is not unique. These complexities exist in nearly every geological environment around the world. Our most common method to account for in situ stress is by oversimplifying and applying average orientation and average magnitude gradients, where we just have an increasing stress with depth, and applying that to our global and our local design. Now, we may have, in some cases, local in situ stress measurements that have been achieved at a mine, or regional understanding of data that comes from literature or resources like the World Stress Map. And we simplify it. We take all of the averages and we say, oh, my average gradient is this many MPa as I get deeper below the Earth's surface. Now, that's common practice. The best practice that we have in defining the in situ stress state as an input for our design process is to rely on strain-based stress initialization, which is a numerical method that effectively applies deformation or strain to a numerical system that is consistent with the strain history of a geological environment. And this allows us to capture a virgin in situ stress state with stress gradients and stress rotations that are more consistent with the natural geological history. It allows the stresses in individual geomechanical domains and across boundaries to initialize in a more natural, non-uniform manner. So I want to demonstrate what this looks like. We're applying deformation to a numerical system. We can conceptually simplify this to the concept of a system of springs. So if you have two springs, a soft spring and a stiff spring, and you apply the same magnitude of deformation to these two springs, we know that a soft spring will inherently have less force required than a stiff spring. So the stiffness variability impacts the load that is required to cause a certain deformation magnitude. So what does this look like in numerical modeling? I'll show you a very simple case study here. Here is a mining environment. You can see mine shape shown on the top left-hand side of my screen in gray. And there's a vertical cross-section cut through this mine geometry, illustrating 3 different geological domains that exist in the area. And the material properties of these 3 different geological domains are variable. They have different strength and different stiffness. And when we apply these to a numerical model using the common practice methodology for uniform depth gradients, we get stress profiles that look like these 2 center images. I have maximum principal stress plotted in the top figure and minimum principal stress plotted in the bottom figure. And again, this is a vertical cross section. So you can see very uniform increase with stress as we get deeper below the Earth's surface. When we look at the best practice of applying strain-based stress initialization, you can see that the numerical simulation produces a substantially different in situ stress state pre-mining. So this is a virgin pre-mining stress state. There are substantial stress gradients as we go across domain boundaries, and even local heterogeneity within the domains according to their geometry in 3D space. So the in situ stress picture is quite different. Now, we may be asking ourselves, how do we draw any type of conclusion around which of these stress assumptions is more correct for our geomechanical design? And the answer is that we must be relying on performance-based design processes so that we can verify our design inputs through observation of true ground reaction. For this particular case study, I can demonstrate performance-based design through calibration and verification. For this particular case study, we have the luxury of seismic data, and we can rely on seismic data to verify our numerical model performance. So when seismicity occurs in a rock mass, it gives us a fully 3-dimensional picture of where the rock mass is going through the failure process at a particular point in time. And we can rely on a fairly simple design verification rule that tells us that in the pre-peak regions of a rock mass, the onset of seismicity will occur when our differential stress is between roughly 30 and 50% of our material UCS. And this is based on fracture initiation literature. We know that fracture initiation starts in a rock around 30 to 50% of the UCS, and that's quite widely published by numerous different authors. So when you have seismic data, you have XYZ coordinates of failure observations within our rock mass, and you can read all of those thousands or tens of thousands of observation points spatially into a numerical model and sample the stress state, the strain state, the yield state, where failure process is observed to be happening in reality. And just as a very simple example on the slide here, I'm illustrating stress state data that's been sampled at seismic event locations. And we know that these seismic events should be occurring when our differential stress is between 30 and 50% of our UCS. So I can statistically evaluate all of this information that comes out of a numerical model and see that my pre-peak elastic regions are in fact producing seismicity within that stress threshold. Okay, this is a fairly simple means to verify numerical model performance. Now, if I look at results for this model particularly, I've got 3 different geotechnical domains. Across the top of my slide, I'm showing numerical results for my uniform depth gradient simulation. And on the bottom of my slide, I'm showing numerical results for the best practice of strain-based stress initialization. And what I can see is that the strain-based stress initialization simulation outperforms the oversimplified assumption that stresses just increase as I get deeper. I have better correlation between seismic onset and my expectations for stress magnitudes according to my measured UCS values for these different domains. And I also have a reduction in statistical variability in my results, which is demonstrating that I have a more reliable numerical system. So the conclusion is the complex stress state can better reproduce observed ground reaction, in this case, as observed with seismic data. Now, I'm going to show you another case study to demonstrate why we need to appropriately capture our in situ stress state in order to understand the fundamental mechanisms of failure and therefore characterize our hazard in our geotechnical hazard correctly. If we don't have the right in situ stress, we run the chance of introducing fatal flaws to our design process because we do not adequately capture the correct failure mechanisms. So here is a case study of a rock burst, which occurred at about in a mine tunnel about 2 kilometers deep. And excuse me, the severe seismic reaction that caused the damage you can see in these photos occurred in virgin development. So they were just advancing a tunnel with very little mining-induced stress changes in the area. There's a geological map in plan view illustrating the geology of the tunnel. You can see there's a number of different rock types present. If you see my cursor, the rock burst happened right in this location where I have a local fault shown in green running just behind my mining tunnel wall. And then I had some local jointing structures shown here with the orientation of the red dashed line and the blue dashed line. And all of this happens immediately adjacent to a significant geological contact between a basalt, which is shown in the green, so very high competency stiff geological unit, and an ultramafic, which is shown in the light blue. So fairly complex geological conditions occurring where this rock burst incident manifested. So To back analyze the mechanisms of this particular rock burst, a local scale numerical model was required. It had to be detailed enough to capture the complexities in the geological units through the area of interest. It had to account for the explicit influences of the local faulting and local jointing on the area of influences, or the area of influence, sorry. And then, of course, we also needed to represent the performance of the ground support system. So in this case, local scale modeling is required to do that mechanistic design analysis rather than taking a susceptibility approach. So to set up a numerical model and evaluate the local scale ground reaction, we have to have some understanding of what boundary conditions need to be applied to this simulation. So the most common practice method would be to say, okay, we're 2 kilometers below the Earth's surface. We know that in this particular mining camp, the gradients of stress magnitude as we get deeper. We know regionally what the far field stress tensor orientation should be, and we could just apply a very simple stress tensor to our model like the one summarized here in the table. The other approach, which is better aligned with best practices, is to develop a regional or mine scale model where we can apply strain-based stress initialization to the geological, all of the geological units in the area, and develop a more naturally complex pre-mining stress state. And that's what you're seeing here on the right-hand side of the slide. And the white star that's illustrated is the rock burst location. You can see it happened in the basalts near the contact with this ultramafic body. And with this strain-based stress initialization simulation, you can see that we have very complex 3-dimensional stress state just based on the geological evolution of this particular mining environment. It's quite complicated with stress magnitudes varying, over 50 megapascals. And sorry, I should back up for reference. This is a horizontal cross section. So all the stresses you're seeing in this figure are at the same depth. And the variability that we see is according to geological unit. So we can take the stress tensor from the common practice depth gradient methodology and the stress tensor that is predicted by best practice strain-based stress initialization, and we can load that into a local scale numerical model. And that's what I'm illustrating here. Again, horizontal cross sections. The white shaded area highlights the location of the mining tunnel. You can see the structure shown here. The white lines are local jointing that's included in the model. The heavy dark dashed line is a fault. Geological contact is in here. And again, that white star is highlighting the rock burst location. And we can see that depending on our assumption of far field stress and our methodology for applying far field stress, the magnitudes of stress and the local gradients in stress tensor are quite different between these 2 numerical simulations. And this can produce a very different back analysis of our failure mechanism, which is what I want to demonstrate. So before I talk about the numerical results, I'm going to give you a little bit of just background so that the methodology for interpretation of rock bursting from a numerical model is clear. When we do numerical modeling, we want to understand how to interpret the potential rock bursting volume. So the background figure here is illustrating basically a tunnel with different zones of damage around the periphery. And if we zoom in to those zones of damage, we have a highly damaged zone immediately adjacent to our excavation. The inner excavation damage zone a little bit further in, and then the outer excavation damage zone even further behind our wall. Now, the highly damaged zone around an excavation it is sufficiently yielded that it cannot carry substantial load anymore, so it's stress shedding, and it experiences volumetric strain that is in extension, so the rock mass has bulked up somewhat. The inner excavation damage zone is also in an extensional state, but it has a bit of confinement on it, so it can carry moderate load. And then the outer excavation damage zone, it remains in compression, and it can carry much more substantial loads. So when we think about strain bursting mechanisms around a tunnel excavation, we know that they can occur generally in this inner excavation damage zone or at the boundary between the inner and the outer excavation damage zone. That's our rock burst location. And so we can look to that for our numerical interpretation of rock burst hazard. So what I'm showing now with the results that are illustrated here is I've got maximum principal stress in the top figures, minimum principal stress in the bottom figures. And in the center of my screen is that common practice, homogeneous stress state implementation with the depth gradient. And then on the right-hand side of my screen, I've got the best practice strain-based stress initialization method. Now, just at first glance, we can see that the numerically predicted stress states are quite different. That's contoured stress shown here. The black isosurface you can show here is illustrating the extent of volumetric strain equals 0. So anything inside of that is in extension, and beyond that would still be in compression. And we can identify our burst volume through this process. So the burst volume is kind of in the top right-hand shoulder here. Now, these results are significantly different. In the constant stress state, the burst volume is not adequately represented. We do not see the high compressional stress happening here. We also see that the damage extent in our walls is significantly smaller. It's about 2.6 meters deep in the common practice stress state, and it's about 3.4 meters deep in our strain-based stress initialization. And that damage depth becomes really important when we think about the magnitude of our strain bursting hazard. If you have a deeper damage depth, you have higher potential to generate larger magnitude strain bursting events because it's deeper into the wall. So we've got a bit more burst burden available for mobilization. And then the other thing that I want to point out here is that the local structures are also playing a significant role in how the stresses are being redistributed around the periphery of our excavation, and again, the damage depth. So from these two models, we see a picture of a much more significant hazard in the model that has the strain-based stress initialization. These results that I have shown on the screen right now are showing us the end state after the numerical model has excavated the entire tunnel. And what these results don't show us is the stress evolution to get to this point. So they tell us that a stress damage hazard exists, but they don't tell us how we got to that point. So the other thing we need to look at in our numerical model results is our strain history. And again, I'll just give you a bit of background information. The stress path that a rock mass goes through as it goes through the failure process is a really good indicator of the potential for rock failure to be violent or non-violent. Okay, so if we cause rock mass damage by stress loading and a crushing failure mechanism, we may produce non-violent spalling or bulking, or we may produce a violent rock bursting event. And stress path is a really good indicator of exposure to rock bursting. If you have a stress path where you have got your rock mass approaching your spalling limit by stress loading, as shown here with the red line, and you approach your spalling limit and hit it at high confinement, you are more likely to produce a violent failure mechanism. Whereas if you have a stress path
No, I'm coming.
Where you have stress relaxation, you are more likely just to produce non-violent spalling or slabbing mechanism. So the stress path is important, and we can query our numerical model to understand the stress path in our rock burst volume. So comparing again our two different far field stress state assumptions, the dashed line represents the stress path for the numerical model with the constant stress state, and the solid line represents the stress path for the numerical model with the strain-based stress initialization. And what we can see here is that our numerical model with the more geologically complex stress state is providing a picture of a much more significant rock burst hazard. So this, I really want to highlight that depending on how we apply in situ stress to our mechanistic analysis, it can really substantially change our interpretation of mechanism, and it can change our interpretation of what type of hazard we have to manage from a ground control perspective. So just to kind of summarize this case study, best practice common stress state for the back analysis of this particular rock burst event, it doesn't clearly establish the correct mechanism of failure. It doesn't produce the correct, or it didn't produce the correct damage that was observed. And so this impedes our ability to understand the fundamental causal factors that led to a failure event. And if we don't understand the right causal factors, it makes it very difficult for us to make informed decisions about how to mitigate this type of risk should it occur in the future. And so this really severely limits our ability to manage this type of hazard, to identify and manage it. With the more complex and geologically realistic in situ stress state, for this particular case study, it was capable of capturing the correct failure mechanism. It produced a better representation of the observed damage, and it allowed us to understand the causal factors, in this case, geological structures, lithological contacts, and joints were all contributing. And then this supports more informed decision-making around risk mitigating strategies and the implementation of engineering controls. So some key points that I will highlight after all of that. Boundary conditions are critical input for our engineering design process in geomechanics and rock engineering. And if we do not have the correct boundary conditions applied to our analyses, we are at significant risk of introducing fatal flaws to our engineering design process. We know that the virgin in situ stress states in most geological environments are very complex. We are data limited. It's hard to characterize, but we know that they're complicated, and oversimplifying often sends us down the wrong path. Strain-based stress initialization is a fundamental best practice in geomechanical design. It has some reliance, of course, on the utilization of numerical models. When we have data available, we should be calibrating and going through verification process with our design tools to make sure that the stress state that is applied to our analysis, it's appropriate. And that's applying, of course, performance-based design procedures. This is mandatory. If you are in a design situation where observational data or monitoring data is not available, then we have to rely more heavily on sensitivity testing. And this should be an absolutely mandatory component of our design to make sure that we understand how potential variability in our design inputs is going to impact our interpretation of design outputs. And with that, I have a thank you to everyone for signing in and joining us today. And I think we have time for maybe a few questions.
Thank you very much, Kathy, for this very interesting presentation. Thank you. We do have some questions in the chat. Few questions and discussions, I think. You can, Alan or Brian, you can turn on your mic and you can ask your questions if you want. Otherwise, I can also if you don't want to do that, I can read your questions.
Yeah, sure. It's Brian Buss here. I'll go first. Can you hear me?
Yes.
Yeah. Great paper here, Kathy, as usual from Rock Engine, the team there. You mentioned something in passing fairly quickly, and it's the question of thermal loading. Just a bit of follow-up on that. You got a lot of practitioners that are dialed into this call and probably made a lot of observations in terms of very tactical, ground control type responses to a high stress environment. But this thermal loading concept, I'm sure a lot of those people have seen this in the field where, on first exposure of the rock mass, you're starting to ventilate. You're in a virgin temperature condition, so the rock mass itself is quite hot. As far as local strain bursting goes, it's probably the most hazardous exposure time is when that rock mass is first exposed, and then the bolting crews are going in, to install ground support. This thermal loading I'm interested in because, we often see it as soon as you expose and bring ventilating air or apply water, cold water to wash down, you start to see a strain response pretty immediate, and it activates a lot of localized strain bursting. So here's my general question. Is this primarily that localized problem of sort of immediate concern, more of a tactical issue, or do you believe it's playing a bigger role in sort of globally changing temperatures in much larger broad-based rock mass itself?
Yeah, I think in a mining context, an underground high stress mining environment context, we do know conceptually, like as you say, you expose your rock, there's a rapid temperature change, you put water on your rock, is that influencing the temperature change? I think managing that tactically is already or should already be covered by our expectations for bursting ground conditions, right? Like you're already in a situation where you have bursting ground conditions, whether or not you spray it with water, it's still going to be highly exposed to bursting conditions. So you should have your controls in place with ground support, re-entry, equipment utilization, all of these things to manage that tactically. So I think actually in mining, we're in a good place to manage that, even though there's uncertainty on how much temperature change is an immediate causal factor, if you will. I have seen work done by others that actually looks at strain bursting conditions in rock masses exposed to sun and atmospheric temperature gradients. I haven't personally been involved in that directly, but I have seen some work done by others. Matt Perra's name comes to mind because him and I had conversations on this a number of years ago, and he showed me some fascinating videos of rock exposures on the ground surface where heating up during daytime temperatures is leading to bursting conditions. In that sort of a situation, nobody has the controls in place to manage the hazard, right? So it's a bit.
Okay, yeah. Thanks for that. Really appreciate it. And otherwise, a great paper today. Really nice to see this type of research being done.
Alan, do you want to ask your questions, or should I go through them?
Well, I can do that. Hi, Kathy. It's been a while. Great to see you there, and great paper there. Thank you so much. I'll just quickly ask the one question I have, definitely for sure, is the consideration of the boundary conditions between those domains, or the spring to spring, the simplified picture there. Thank you for that. That's excellent. And just wondered how much that needs to be taken into account, and primarily because in my view, at least anyways, and some experience I've had, definitely post modeling and calibration at those locations seems to be quite an important item to follow up on, and that those reactions are at those areas, however thick, maybe on a case-by-case basis, but however big those boundary conditions are, they seem to be play a big role in the overall rock mass stability.
I'm sorry, you're asking for?
I'm asking how much in your modeling are you taking into account those boundary conditions?
Oh, hugely, hugely. Like the amount of time that is spent on establishing the boundary conditions in a numerical model, in my opinion, outweighs the amount of effort that goes into establishing our material properties. We tweak our material properties certainly, but with material properties and constitutive behavior that we assign to numerical models, we've got lab testing, we've got rock mass characterization, we've got monitoring data that often tells us something about how the ground is deforming. So we have a bunch of data collection that helps us narrow in on appropriate inputs in terms of material properties, right? We might have a little bit of uncertainty in how strong a rock is, but we've got it pretty well bound based on the data that we can physically collect. But we don't have that same bounds on in situ stress. And so I believe you have to put a lot of effort into testing how much you don't know about in situ stress so that you can understand better how much it influences your numerical outputs, right? Like changing something by 10 MPa can substantially change the failure mechanism that you're imposing on a tunnel. And as I've demonstrated today, you can change your in situ stress by 10, 20, 50 MPa over very short distances underground just because our material stiffnesses are varying. And so like these are significant variances in stress magnitude that are proportionately much poorer bound than our material properties.
Great, thank you.
Thank you, Kathy. We have another question from Hadi. Hadi, do you want to turn on your mic and ask your question?
Yeah, I'll go on. Thank you so much. Thank you for presentation, Katie. I just am curious if you have any suggestion, idea for initializing the strain-based loading approach for the case of a deep mine under the coupled effects of high pressure, high temperature, that we don't have the possibility of appropriate instrumentation measurements for such a purpose.
For the numerical methods for initializing the stress? Is that what you're asking?
Yeah.
Yeah, so to apply strain-based stress initialization to numerical model, you have to apply a deformation to the numerical model, and that induces strain, and then that induced strain is what is generating the in situ stresses. So instead of just like turning on stress according to what gravity should be, you have to actually ramp up your stresses by applying a deformation to your system. There's different methods numerically, depending on what type of code you're using and what type of model you're building. Rockenge actually has a patent pending for the methodologies that we use in-house for doing this. But you're just effectively applying a deformation and letting that deformation go through your numerical system. Your system comes to equilibrium, and then you can sample the stress tensors that have been imposed.
Thank you.
And will such an approach work even for the coupled systems?
For systems that are not coupled, like with hydromechanical coupling, is that what you're referring to?
Yeah, I mean the multi-phase systems and the coupled multi-phase system.
I don't see why it wouldn't work.
Okay, thank you.
Yeah.
We have another question from Hussein. Hussein, would you mind to turn on your mic
Yep.
and ask your question?
Thank you so much, Kathy, for a nice presentation. I'm just wondering what are the key factors in selecting proper boundary strains and how those boundary strains can be verified?
Right. So if you have an idea of what your global stress state should be, right? So generally, regionally, we know the orientation of our in situ stress tensor, and we generally have an idea of what our K ratios are, so our ratios between like horizontal and vertical stresses. With that, if you have your material stiffness properties, so your rock mass modulus and your Poisson's ratio, then depending on what the geometric extents of your numerical model are, right, like your XYZ dimensions, you can just back out how much movement you need to apply And then it's just a stiffness calculation, right? Like stiffness, stress, and deformation are your key inputs to calculating the magnitude of deformation you have to put into your system to ramp up your stress targets. And you have to
Thanks,
account for
and
your Poisson's effect, because when you squish it in one direction, it squeezes in the other direction. So
thanks for the first part. Would you kind of verify those generated stresses in your model against local measurements then?
oh, absolutely. That's
Okay.
part of your calibration process.
Okay. Appreciate that. Thank you.
Eliane, you have a question. Do you want to ask? The question is, which software was used to perform the numerical modeling done using the strain-based stress initialization?
The modeling work that I showed in the case studies today has relied on FLAC 3D. But you could apply this to any continuum or discontinuum method. It wouldn't work for, I don't think it would work for a boundary element because you don't have the continuum components of it. But you could apply it to a continuum code, you could apply it to a hybrid code, as long as your synthetic rock mass, whatever that looks like, has stiffness parameters.
Okay, thank you.
Thank you, everyone. Any other questions? If you have any question, please raise your hand and turn on your mic and you can ask your question. If not, I think Kathy could be available through email. If you have any further question, you can email Kathy. Oh, there's one question from Masood. Go ahead, Masood, please.
Hello, thank you so much, Kathy, for the great presentation. I have this question with regards to the locked-in stresses. So you mentioned that you used the constant K values based on the measurements. When you consider that, then at the surface of the ground, as soon as you have sigma z equal to 0, horizontal stresses are 0 as well. Which is not following up the correct kind of locked-in stress consideration. I was wondering if you consider that locked-in stress value in your model.
Yeah, so if you're doing strain-based stress initialization and in your model actually represents the topographic surface, you automatically get that change in K ratio with depth, right? Like your K ratio changes with depth. Just as it does naturally. And if you're using the more common practice of stress initialization, you can apply varying K ratios with depth by just, as you say, like adding in a constant component or making your topographic surface like a free surface in your numerical model. So there's a few different ways to manage that when you are simulating something that includes representation of the topographic surface. And you have to be particularly careful when you're in mountainous terrain.
Yes, absolutely. So even with doing that, if you are there in the mountainous area, if you consider the ground surface in your model, then again you need that horizontal locked-in horizontal stress there. So that you have the gradient, you have the magnitude right at the surface. Otherwise, you will get 0 stress, horizontal stress at the surface. If you don't have the mountain, for example, in Toronto area or wherever you have flat surface almost, not much topography there, then you get wrong answers. So I was wondering if you consider that in your best practice, not common practice. So for that pattern that you were mentioning, I was wondering if this locked-in stress and its variation with regards to the layering of the rock is something that consider in your model. Thank you.
Yeah, and it's accounted for. And when you're doing stress initialization in mountainous terrain or an area with highly variable topography elevation, then you have to make sure that you're accounting for your K ratios and your gravity. And when you initialize your model, you'll actually see that your stress tensor should rotate so that your in situ stresses are your highest stresses are parallel to your, or in the plane of your local topography. So you see significant stress rotations in your simulated stress state when you're in near surface and mountainous terrain.
Thank you.
Maybe the last question from June. Go ahead, please.
Yeah, thank you. Hi, Kathy, thank you so much for your presentation. It's very interesting. I think I have two questions. First, I'm still a little bit confused about the stream-based method. So if I understand you correctly, so first of all, we have a general idea about the in-situ stress magnitudes and orientations. Then we can back analyze the orientation and the magnitudes of the strains to be applied on the boundary condition. Am I right?
Yep.
Yeah, okay. Thank you. My second question is regarding, as you know, for such large like a geological model or domain, many times we have different, subdomains, or as you know, for the Canadian shield, we have three, stress domains, and in each domain we might have different, stress orientations. So I'm just wondering, do you have like any experience in like applying the strings, different orientations of strings along in one model? For example, from the ground surface to like 300 meters deep, we apply the string in one direction, and below 300 meters deep, we apply the string in another direction.
Conceptually, there's no reason you couldn't do that. You'd have to see how your model came to equilibrium. You'd probably have to be a little bit careful. I personally have not done that. I would say though, if you have stress testing data that is telling you that in different domains or different areas of your mine or your project, you have different stress orientations, I would look at regionally what my stress tensor is. I would apply strain-based stress initialization with a well-represented geological model, and I would see if I couldn't evolve those stress tensor rotations naturally, just based on the like regional far field expectations for loading. Because maybe there's a geological boundary or a geological structure that is leading to why you have different stress tensor rotations or orientations at different points in your testing program.
Okay, yeah, thank you.
Thank you so much. If you have any further question, you can reach out to Dr. Kalinchak. There's an email that's been indicated here in this last slide. This presentation also has been recorded and is available for you to watch again at your convenience. You can find the recording on the CIM's YouTube channel. I would like to thank you again, Kathy, for this very excellent presentation. Thank you so much. So please stay tuned for our next webinar, which will be announced soon. Thank you so much. Have a great evening.
Thanks, everybody.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Have a great weekend.